Thank you, Peter. Okay, so first some acknowledgements. Firstly, yes, to acknowledge this work was done at the University of Southampton in my previous life, so to speak. The work was funded by the Institute and Faculty of Actuaries, so thank you very much for that. And that funding helped in particular to fund the work of Xiaoling Wu, who was a research assistant on this project. Xiaoling's not here today, but she did much of the heavy lifting associated with the computation that underlying the results of this. So what am I going to talk about to set this in context? Well, I'm not going to dwell too much on this because I think I'm in an audience where that appreciates that mortality forecasting is important, and that in particular mortality forecasting is shrouded in uncertainty, and that quantification of that uncertainty is an important aspect. And there's been many good and detailed studies looking at different models, looking at the different uncertainties that those models imply for future mortality, but perhaps, as Peter said, not so much really on how one might account for that model uncertainty in coming up with a forecast which represents what we believe about mortality going forward. So, a little bit of data. So here's some data that I'm going to focus on. There's nothing special about these data, but they're useful data for the purposes of illustrating the methods that we've developed, that we've investigated. So YXT are going to denote death counts, in this case for males in England and Wales, over a series of age groups X, which we're going to just take pensioner ages here, 60 through 89, not looking at the very advanced ages, and over a series of time periods, in our case, ranging from 1971 to 2009. So here's a sort of graphical description of the data. What we've got here is the log mortality rate plotted as a function of age for each of those years. So there are 39 lines there, and obviously mortality generally improving. So starting at 1971 and coming down through 2009, and sort of the effect of the sort of oft discussed 1919 cohort appearing there as progressing through the data. So these are the data that we're going to consider modeling, or going to consider models for. So let's start with a standard familiar model on which I want to base my discussions. Talking about this model is purely for the purpose of discussing the kind of uncertainty concepts that will be important in this presentation. So let's take the Poisson-Lee-Carter model with a random walk effect for way of forecasting the period effect. So what we're assuming here is that the death counts, the Y's, they're Poisson distributed, depending on in this case, these are approximate mid-year population counts, the exposures EXT, with death rates mu, and that the death rates are going to be modeled. This is the classic Lee-Carter model. The log, we have this log bilinear model for death rates, depending on an age profile and a sort of linear bilinear age-time interaction. And that if we want to use this as a forecasting model, because it has a time parameter in it here, kappa t, t index is time, we're going to want to know how that evolves into the future. Then we're going to have a model that projects what happens to that in the future. So this part here, essentially I'm going to call the projection model. This part here is just a simple random walk model for kappa. That's not the only model we might consider, but that's the one that I've just written down here for the purposes of this discussion. So these two final equations here describe a random walk model for kappa going forward. This describes what I'm calling the rate model, the structural part of this Lee-Carter mortality model, and this part here describes the Poisson variation. And so I've already sort of got onto my next slide, which is to say that there are a series of different kinds of uncertainty in these four equations here. The first of which I'll call natural uncertainty. Philosophers of science sometimes call this aleatory uncertainty. It's the uncertainty that can't be modeled away. If I was to observe the same year twice, I wouldn't get the same answers, in parallel universes, if you want to think of it like that. And that's what the Poisson part of the model is telling us. That's the sort of, that's sort of uncertainty, variability that I can't model away. And then there's the parameter uncertainty. So this natural uncertainty depends on some parameters, some mortality rates mu, and I'll model those parametrically as functions of other parameters. In this case is my alpha, beta, and kappa. And these things I don't know. I have to estimate based on my data. And so I have uncertainty associated with what the values of those are. Not just the values of the parameters in my rate model, but also the parameters in my, what I'm going to call here, my projection model. The model which projects forward any of the parameters that I need for future time periods, or as we'll see later, future cohorts, in order to do projection. So that's parameter uncertainty. And then finally, the part which is really the focus of this work, the model uncertainty, the fact that I don't know that this is, I won't say the right, there's an oft quoted phrase that all models are wrong, but some models are useful. So there's no sense in talking about a right model, but we don't know that really that this is the best or most appropriate model. So I'm uncertain about whether this is the best model to use for the rate part of the model, and I'm uncertain about whether this is the best model to use for the projection part of the model. So it's that model uncertainty which I'm really interested in this work here. Okay. So what models am I going to look at? What's going to be my universe of models for the purposes of this work? Well, it's going to be these models that were looked at by this paper by Dowd, authors including Andrew here. The six models, M1 through M7. You'll notice there's an M4 missing here, and I'm going to restrict my universe of models to models that essentially can be, well, firstly, stochastic. These models are all stochastic in nature. In order to adopt the approach that I'm talking about, the models have to have we have to have underlying stochastic models. But I've also restricted to models of what I've called fixed dimensionality, and so excluding sort of smoothing type, spline type models, of which M4 here is a case. So here are 6 models that I'm going to consider. I'm going to suppose that my universe of models I'm going to consider are these 6, and I'm going to look to see how I might integrate my uncertainty about which of those 6 models is the most appropriate into forecasting. I don't have time particularly to talk about those models in more detail, but you'll see that they all have particular features. They all have some dependence on age. They either have a non-parametric dependence, sort of factorial dependence on age, or they have a functional dependence on age. They all have parameters that depend on time, the kappa t's here, so time parameters which will have to be forecast forward to future time periods if I'm going to use these models as forecasts. And some of them have cohort parameters, and these are what these gammas represent, so parameters that follow through particular cohorts in the data. And again, those parameters will, if I'm going to use the model for forecasting, will have to be projected through as well, because I'll want to make inferences about future cohorts whose data I've not observed. Okay. And so those are what I might call my rate models. Okay, the first part, if I go back to the previous slide, those are possible alternatives for that line there, and then possible alternatives for this part of the model. Well, any time series model in particular could be used for projecting forward either period effects or, as I've written here, cohort effects. So in particular, simple, what we might call a ARIMA 010 model, which is just a random walk model, okay, or more complicated ARIMA models, ARIMA 110, where the first differences, in this case of the cohort effects, follow an AR1 process. And you can make these models as complicated as you want, or as complicated as as are deemed necessary when looking at your data. Okay. Again, I'm going to consider a rather limited universe. Well, I'm going to assume that I don't have any model uncertainty about the projection model for kappa. This is a common and follows the Dowd et al. Approach. I'm going to assume that's ARIMA 010. And I'm just going to consider 2 possible different ARIMA models for the uncertainty about the cohort effect. Okay. So my model uncertainty relates to which of the 6 rate models, and for those with the rate models which have a cohort effect, which of these 2 time series models might be appropriate for the projecting forward the cohort effect. Okay. And the approach I'm going to take is a Bayesian one. Okay. So why Bayesian statistical inference? Well, Bayesian, the sort of fundamental principle of Bayesian statistical inference is that if I've got uncertainty, I quantify that uncertainty through probability. That anything I'm uncertain about, I represent that uncertainty through a probability distribution. And in particular, it's a very natural approach if I've got different sources of uncertainty that need integrating, as I have here. So all uncertainty is quantified through probability distributions, including my 3 sorts of uncertainty that I talked about earlier. The natural uncertainty, which is represented through the likelihood, okay, the fact that I've got a probability distribution for y given the parameters, in this case the Poisson distribution, given the particular mortality rates. the fact that I've got parameter uncertainty, i.e. uncertainty about the model that drives those rates, and the forecast model for the rates. So parameter uncertainty relates to both those parts, and I'll talk about that a bit more in a minute. And so that uncertainty a priori, before observing any data about those parameters, is expressed through a prior probability distribution, and those of you, I hope many of you are familiar with at least the basics of Bayesian statistical inference, which says that we update that prior probability distribution for my model parameters to a posterior probability distribution through this equation here, Bayes' theorem. So this represents my uncertainty about the model parameters having observed data, and it's proportional to the product of these two expressions here, my likelihood representing the natural uncertainty, my prior distribution representing my uncertainty about the model parameters before observing any data. Okay. And so it's what I'd call coherent in the sense that we can simultaneously integrate the uncertainty, even just with a single model, we can simultaneously integrate the uncertainty both about the rate model and the projection model into a common, a joint posterior distribution representing my uncertainty about all the parameters in the model. So the rate model and the projection model are what I would call fully integrated. So all that is left is for me to compute the posterior distribution using Bayes' theorem from the previous slide. How do I do that? Well, it's not quite as straightforward as it looks, as those of you who are familiar with this kind of approach, I'm sure will agree, is that, but we have a suite, we have a sort of common tool these days of Markov chain Monte Carlo, where instead of doing complicated analytical integrations associated with highly multivariate probability distributions, we just essentially generate a random sample representing our uncertainty about all the parameters in the model. So in this Lee-Carter sense, about all our alphas, betas, kappas, and the parameters of the projection model, the parameters driving the random walk. We generate a sample from that joint probability distribution, and that sample is then stands prepared for any inference, and in particular, as we'll see in a minute, any prediction or projection that we might want to do. Okay. And this is not an entirely new approach within a mortality forecasting framework. Certainly the papers by Chardo et al. And in the book by Girosi and King, they've applied Bayesian methods and Markov chain Monte Carlo computation to exactly this kind of setup. So as I alluded to a minute ago, in particular, having a sample from the posterior distribution or being able to compute with the posterior distribution sets you up in order to do projection or prediction. So it's particularly natural for projection, as what we need to compute, what the Bayesian approach tells us we need to compute. Remember, all uncertainty is expressed through probability. So our uncertainty about future mortality rates or future mortality counts is represented through the predictive distribution of the future mortality count given the data that we've observed. And how do I get that? It's just really the best way of thinking about this is as an average. It's an average of what each of the individual parameter values would tell me averaged over my uncertainty associated with those parameter values, in other words, my posterior distribution. And if I've got a sample from the posterior distribution, this just then becomes a sample average. Okay. And I base my best estimate typically on the mean or median of that sample, and I base my uncertainty typically on quantiles of that sample. 90% interval, then I take the fifth quantile and 5th percentile and 95th percentile and look at the interval between the two. Okay. What about model uncertainty? Well, model uncertainty in the Bayesian framework is just integrated in exactly the same way. So again, we've got uncertainty, so how do we express that? We express that through a probability distribution, so we have an a priori probability distribution. If M indexes my model, so M, you can think of M as being 1 through 6, or 1 through 7 without 4 in this case, representing the different models, then we assign a prior probability to each of the models. Now, typically, I'll just skip to the bottom line here. It's typical in a model uncertainty framework, we don't think very carefully about what we think a priori about the models. We assume them to be equally likely. And then how do we update those prior model probabilities to a posterior model probabilities when we've observed our data? Well, we just do it using Bayes' theorem. Okay. Now, Bayes' theorem now says, here's my posterior probability for my model. Given my data, y is proportional to my prior probability multiplied by this thing here. And what's this thing here? It's the marginal likelihood. It's the probability of the data given the model. And I get that by averaging, according to my prior distribution for my model parameters, the likelihoods for each of the models. Okay. So it's a computation that can be a little tricky to do, but in principle, it's straightforward. Okay. And here are some computed marginal likelihoods. So I'm just focusing on this, because I'm going to assume that these are all equal, these prior model probabilities. So let's look at these marginal likelihoods. What do they come out to be? Now, the thing about these is ignore the values. All that matters is the differences, is what these things are relative to each other. And these are on the log scale. Okay. So if you want to think of how likely these models are compared with each other, think of differences between these and exponentiating them. So some of these differences are absolutely enormous. I mean, you look at the difference between 11,800 and 7,300. It's a difference of about 4,500. If you exponentiate that, you get, a big number. So some of these models, a posteriori, having observed the data, are very, very improbable. Okay? And some of the models are much more competitive with each other. So the highest values, because these are all negatives, the highest numbers are here, M6 and M7. So typically we get relatively small differences between the projection parts, but big differences between the different structural parts, the different rate models. And that's typically the case. I've omitted here M2 because, as with other authors, M2 proved to be tricky to compute. So if you didn't observe what M2 was, it's the model which it's a sort of Lee-Carter extension which has two bilinear terms, one involving a period effect and one involving a cohort effect. And this model is often found to be multimodal, and multimodal tends to cause problems with your Markov chain computation. So that defeated us doing that model. But at least we did manage to get MCMC computation and marginal likelihoods for the other models. Okay. So when I've got those posterior model probabilities, how do I integrate them into a common projection? Well, again, the probability calculus just tells me how to do this. If I want a posterior probability distribution, okay, for a future death count or a future death rate, given the observed data y, then what I do is I just take a mixture of what I would project under each of the individual models. That's what this thing is here. That's what I had on the 2 slides ago. That's, 3 slides ago, that thing here. Okay, my projective distribution under my forecast distribution under a particular model. Well, I take each of the forecast distributions under each of my models, and I just average them, okay, weighted by the posterior model probability. So the higher the posterior model probability for a model, the more it contributes to my belief about how mortality varies going forwards. Okay, so we get a mixture. So in particular, looking at these numbers here, if I do that for these models, then these models which have very small, very high negative marginal likelihoods will contribute almost nothing. Well, basically nothing, because by the time you've exponentiated 4,000, you've got minus 4,000 in this case, you've got 0. Will contribute almost nothing to the final model average posterior, and basically all you're getting really, if you consider these 8 models, is you're getting a major contribution from the most probable model, i.e. M7 with the random walk projection, with a little bit of the same model with the ARIMA projection. So we're not getting a lot of model uncertainty. So although I'm integrating with respect to a distribution that's basically putting almost all its mass on one of the models. Okay. So here we are. These are some examples of the kind of thing we get going forward. So remember, M6 and M7 were my most probable models, and here they are, if you want reminding of them. And so this is the model that comes out on top. Okay, and this is a forecast mortality curve for age 75 going forwards, based on the historic data, and then going forwards about 50 years. And the funnel here represents a 90% interval, probability interval, posterior predictive probability interval for what mortality is going to look like. So this is my uncertainty, my integrated uncertainty for each of the models. And we are adding something here, I believe, because we're integrating over both the forecast model and the rate model, okay, the projection model and the rate model, which is not typically done. Now, if I want to include the third aspect of uncertainty, I integrate across models, then this is what I get. On the next slide, this is my model average, but really, if I was to plot that on top of this left-hand panel in the previous slide, I would get very little discrepancy because almost all my posterior weight is going on that left-hand model. Okay. And here's another different kind of way of thinking about projections. So here's the forecast mortality curve for 2030 across all the ages that I've looked at. So in other words, this is looking at, remember the data started at 1971, moved down through 2009. Well, the solid red line here is what I expect that curve to look like in 2030 according to each of these 4 different models. M7 with the 2 different ARIMA projection models, M6 with the 2 different ARIMA projection models. These were the only models which were really competitive at all with each other. And then I've got the projection, the median, posterior median, together with the dotted line, the dashed lines there, representing a 90% prediction interval. And again, here's the model average, not looking very different from what I would have got if I'd just taken M7 with the random walk projection. So those are the results essentially of the research. So how would I like to sell it? Well, we've established a framework for fully integrating uncertainty into model forecasts. Okay, parameter uncertainty, natural uncertainty, in particular parameter uncertainty about both parts of the model, the rate model and the projection model together, integrated going forwards. In particular, any correlations between parameters are also accounted for in projections. So in particular, if you've got a cohort effect and a time effect in your model, then the way in which those parameters of those parts of the models are typically correlated, that's accounted for in the projections going forwards. But also model uncertainty, although as you've seen, at least in the universe of models that we've looked at, there isn't a lot of model uncertainty. You tend to come down on a particular model. How would I like to develop this further if I was to take this further? Well, one question, of course, is why don't I get much model uncertainty here? And I think the answer is, or at least my interpretation of the answer is that the reason we don't get much model uncertainty here coming out here is because, at least by conventional measures of goodness of fit, these models don't fit. I mean, if you look at the Dowd et al. Paper, essentially, on a strict goodness of fit basis, the models don't fit. Typically, the data are over-dispersed relative to the models. It's the Poisson part of the model which fails. Now, if you accounted for over-dispersion, I believe more models would come into play. And the reason is this, is if you think of an undispersed model, essentially the likelihood surface is too curved. Okay, so what does this likelihood surface that's too curved do? It accentuates differences on the log scale between models. And we've got very big differences on the log scale between models. If we had a more realistic, flatter likelihood surface, then you get more models coming into play with smaller differences between them on the log probability scale, I think. Okay, that's a conjecture. So I think that accounting for that over-dispersion with more realistic models that did that, you would get better, you'd get more models coming into play. Yes, I'd like to expand the range of models used, consider those semi-parametric smoothing type models that exist in the literature, and potentially other time series projection models. That's pretty straightforward. And then, fully use the Bayesian framework. Here we've used rather diffuse, flat prior distributions, but you could perhaps usefully incorporate other aspects of prior information, in particular where you've got factorial parameters representing an age structure. You can incorporate some smoothness into that using a prior distribution. So that's where, if I had more time, we would have taken it further forward. Thank you.
Can I ask a quick question then,
Sure,
John?
yes.
I mean, in terms of kind of practical application, I mean, the work you've done, I mean, is it computationally intensive? What packages were you using? How can people get into this?
It is computationally intensive, but we did everything in R, and on a fairly unsophisticated laptop, you can run these models in depends what you believe is a reasonable time. The MCM's Markov chain Monte Carlo computation, you can run it as long as you want. But in order to get decent answers for within model yeah, it's not minutes, but it's not days. It's sort of a few hours, 2 or 3 hours, you can get decent answers. In order to get the posterior model probabilities, you have to make sure you've got a really long enough run. So I don't know, I was a bit belt and braces on that. I tended to run it for a lot of hours. But this was on an underpowered laptop, really. So I think if you had a better laptop. But the code-wise, it's all in R. So you know, and you know, I believe, you know, as part of the results of the project, it will be made available. Not very sophisticated R code, i.e. not heavily commented and things like that, with a very caveat emptor and all that. But yes, it's you know, it's not very inaccessible.
Okay, thank you.
I hope.
Thank you, Matthew.
Oh, thank you very much. Very, very interesting. This question is probably slightly out of scope, so I'm not sure how you're going to deal with it. But I mean, one thing of particular interest in this subject, as you may be aware, is what happens when you take the results of this sort of modelling and apply it to a slightly different population. So in other words, the question of basis risk. I just wonder whether your sort of work in this study has actually sort of shed any light from your perspective on how to sort of quantify or better understand that aspect.
Well, I suppose there's two aspects. I think one is, of course, if you've got a different population under study, you can do the same. You can do the same, you know, analysis, but then you get two different sets of results, and the extent is to what extent should one be learning from the other. Yeah, I know I haven't answered that question, and I wouldn't know without having done it. I wouldn't want to hypothesize too much about the best way of doing that. But yeah, for any population you wanted to project forward, you can essentially run this approach. I mean, this was just a particular data set that's used as an exemplar. But whether, if you had two populations that you were interested in, you know, ideally you should be able to integrate that and do some cross-learning. But that's not something that we looked at.
So thank you, John. And it's very interesting to see what you're saying about model risk, where you're comparing the projection throughout time against the data you've got. I guess in a pensions context, a lot of the risk that people are concerned with is not, is our projection going to be correct for the rest of time in terms of predicting when people will die, but what is the risk that it's going to change over the next 1 year or over the next 3 years? As the next 1 year or 3 years of data has come through and we apply a certain model to update our projections, what is the risk that that's wrong because we have the wrong model? Do you have any kind of insight in terms of that risk from the research you've done?
No, I mean, no, not really, because in a sense, what this model integration will do is it'll give you some confidence that your projection is okay, given that one of these models is true. Or not, true is a bad word to use in models, of course, but given that one of these models works. Now, of course, what if, as you say, what if your worry is that really, you know, my universe, which is pretty limited in this case, doesn't include the model I should be using? Well, no, there's no there's no, you know, what we're not talking about here is you know, validating this in any sort of external way like that. So there's no sort of goodness of fit you know, intrinsic in this, or sensitivity intrinsic in this. The robustness it's giving you is robustness to a class of models, to the model being within a class. And of course, the bigger you make that class, the more robustness you'll get. But no, you still, you know, if all of these models were terrible, then you would still be in trouble.
Is that using the likelihood function that doesn't penalise the models with more parameters, just naively, you'd have to say some sort of information criteria to penalise just adding extra terms to an existing model? Is there not the danger that, by definition, this approach, the model you end up giving most weight to in projections is the model with most parameters?
No, because there's an intrinsic Occam's razor here, and it's basically in the marginal likelihood. So the marginal likelihood here is not a maximized likelihood, it's an integrated likelihood. So let's go to, so this, no, hold on, go. Yes, this thing here, this marginal likelihood. This is integrated likelihood with respect to the prior distribution. So essentially, you're penalized with respect to prior uncertainty about your parameters. And actually, if you're familiar with information criteria, the BIC, the Bayes information criteria, is called the Bayes information criteria precisely because it sort of approximates a marginal likelihood calculation. So it's more subtle than just having a simple deduction from a maximized likelihood. But no, you're not comparing models by maximized likelihoods and marginal likelihoods. There is this intrinsic penalization, Occam's razor.
Thank you, John, for the presentation. The question was quite simply, one of the areas of model risk I get further exercised in my is what happens about the over 89-year-olds. If we think of an annuity portfolio for 65-year-olds, we expect to live to 85 plus anyway, so what the model's saying beyond age 89 is actually fairly fundamental to
Yes.
the problem. And obviously with data not extending out beyond age 89, that leaves us a rather pivotal paradigm. How do we model it, and how much model risk is there about that in the absence of information?
Yeah, the approach remains the same, but yes, the less data you have, the better models you've got to have in a way, or what my project was not about was coming up with models, because we were just relying on models that other people had come up with, and as I said earlier, this approach will only be as good as the models you put into it, and that becomes more difficult as you get data which is intrinsically more difficult to model. So yes, I'm sort of sitting back here and saying, bring me good models to put into my approach, because there's nothing about this approach which will save you from not having good models. And as you say, in the hardest data, that's potentially the hardest problem.
Okay.
So, well, thank you very much for the introduction. So I'm just going to give a very brief introduction to the bit of research that we've done, and Torsten will talk you through the detail of the work that we've done. So just by way then of introduction, so here are mortality rates, and we're here looking at a number of different countries, and these are mortality rates over time, but just for age 70. And of course, what you can see from this is that the mortality rates in different countries are all at very different levels, and that these differences, to some extent, persist over time. But also, you can see that there's a gradual downwards trend in these rates. But to some extent, there's if you look at the thick black line and the thick blue line, which are the United Kingdom and Canada, that perhaps there's a little bit of a closing of the gap between these two countries, and so on. So there's lots of interesting things going on there, and what we're trying to do is to think, well, are these just intrinsic differences between these different countries, or perhaps are there particular other bits of information that you can gather within different countries, consistent bits of information in different countries that might help to explain some of these differences? And the thing that we've focused on in this particular project is smoking prevalence. So, because as you all know, that smoking is certainly not good for you in terms of mortality rates, and so perhaps some of the differences between these different countries is down to smoking prevalence. So this graph here just gives a brief introduction to the sorts of data that we've been looking at and using as a way of explaining the differences between the different countries. And so with the United Kingdom and Canada, once again, in this plot, you can see that there's a bigger gap to start off with, so a higher rate of smoking in the United Kingdom, and that gap is perhaps closing slightly over time, but again, it's a case of if we use more of the smoking prevalence data, is it going to help us to get down to these differences? So the objectives for the talk and the research that we've done, rather, are to, first of all, develop a consistent model for the mortality experience, and I emphasize the consistency there across different populations, and that can then be used for scenario generation. We want to think about, can we explain, using this consistent framework, can we explain differences between mortality in different populations, and in particular sort of identify common factors, be it smoking or perhaps other things, which are influencing the mortality in different populations. So with that, I'll now hand over to Torsten.
Well, so as Andrew just said, the aim is to find a model which simultaneously looks at the mortality experience of different populations and then use or to try to identify some common factors which these populations all have in common and which can then be used to reduce the number of parameters in such a model. And the example we have chosen here is smoking for the reasons that Andrew just explained, but also because for smoking, at least, we have some data available. There's this history of smoking prevalence available, and smoking is also, so to say, maybe the most popular, so to say, subject or the most popular factor which kind of impacts mortality. And as people say, smoking is also one of the major causes for statistics, actually. You know, that's there are so many data available for that, which we not have available for other causes, other kind of lifestyle factors. Well, to build the model now, what we first look at the data, and in particular, we look at the data that we have and the data that we don't have. And what we have is clearly we have the number of deaths in different countries. So the DIXT here denotes the number of deaths in country I. The I is the country index here, X is the age, and T is the calendar year. Okay? But what we don't have is the number of deaths among non-smokers and smokers. There are some statistics available looking at some kind of subpopulations and so on, but there are certainly not good and long histories of deaths among non-smokers and smokers. We only have the total number of deaths in a country. We also have the exposure to risk, obviously, as you all know. We can then calculate the mortality rates, deaths divided by exposure. But again, we can't calculate the mortality rates for non-smokers and smokers directly because we don't have the deaths for the counts for smokers and non-smokers. But we do have a smoking prevalence, the SIXT here, so again, that's the same or a similar notation. SIXT is the smoking prevalence as a percentage of people who smoke at a certain age X in a certain calendar year in a country I. And we then think of the number of smokers, so to say we take a proxy here for the exposures the exposures among the smokers. We take that proxy, which is smoking prevalence times total exposure, gives us something like the number of smokers or the exposed to risk among the smokers. So if we want to build a model, then what we start with is to say this kind of simple, intuitive relationships that the total number of deaths is the sum of the non-smokers who die and the smokers. And if we then replace the number of deaths here, DN and DS, if we replace them by the appropriate rates, then we have the mortality rates for non-smokers times, so to say, the exposure among the non-smokers, which is this factor 1 minus S times E. And the same then for the smokers. So the first simple relationships that we get here is in the bottom, so to say, formula here, this last formula. And it tells us that the total mortality rate in a country I, age X, calendar year T, is something like a weighted average between non-smokers' mortality and the smokers' mortality, or in other words, it's the non-smokers' mortality plus some kind of extra mortality here for the smokers times the smoking prevalence. So what we would expect to see is that the more smokers there are in a certain country, the higher the smoking prevalence is in a certain country, the higher is the overall mortality rate in that country. And that's the basic idea. Now, basically, that is not a model, but it's just a trivial relationship. To turn it into a model, we make a number of assumptions, and I have just put on this slide here maybe the two most important assumptions, so to say, that we make here. And the first one is that smoking prevalence has the same effect on the mortality rates in all of these countries. Okay, so an extra, so to say, 10% of smoking prevalence will have the same effect on the mortality rate in all of these countries. And the second assumption that we make is that the total mortality in a country is given by the mortality for non-smokers and smokers and smoking prevalence, but that total is then adjusted by what we call a country effect. In a sense, it's something like an error term. And these two assumptions bring us to the model here. So this is our basic model here. This is this formula here. So what we see here is that MN and as well as MS, they are not country specific anymore. We assume that they are the same for all of these countries. So there's no index I in MN and MS here. What makes, so to say, the overall mortality country specific is the smoking prevalence, which is the SIXT here, this bit here, but also this country effect, which we have here as a multiplicative factor, the exponential of gamma IXT. So the gamma is what makes this, so to say, the gamma absorbs all the country-specific information which is still contained in the mortality rates and which cannot be explained by simply smoking prevalence. Now, when we look at this equation here, what it looks like is like a simple linear regression, with the exception that the error term is here not additive, as you would usually have in a regression model, but it's multiplicative. But that's, you know, it's just, and basically it's still kind of a linear regression. So what we can try is we can actually plot smoking prevalence and the overall mortality rates in a kind of regression-like scatter plot, and this is what we get. So the different letters here, it's just an abbreviation for the different countries that we looked at. We looked at 10 countries, and where you see them here. Okay, so on the x-axis we have smoking prevalence, and on the y-axis we have the mortality rates in those countries at in a certain year and for a certain age. Okay, you see the age up here. You know, it's 1990 and age 60 for the right-hand plot, for example. So we fix the age, we fix the calendar here, we look at the 10 countries, and what we want to see is a regression line. Okay, well, in these plots we can put in a regression line. It looks like that, but clearly it's very disappointing. Yeah, it's a very poor fit. Yeah, this is not, so to say, something that you would call a significant slope or anything. You know, it's a very poor fit. And when we started with this project and we came to this picture, we were basically about to give up. Okay, we were basically saying, all right, well, maybe smoking on a population level doesn't explain mortality rates. You know, more smoking does not necessarily mean more people die. Okay, but then, you know, what we have to keep in mind is that these pictures here are for a very specific year, 1990, say on the right-hand side, and an age, 60. Now I can make a similar plot for every age and for every calendar year. Yeah? And then for each of these plots, I can do that regression. And what we did that basically, and what we looked at is the correlation between smoking prevalence and mortality rates for all the years in our study and all the ages. Okay? And what we came up with is this plot here. So on the x-axis now we have calendar years, and on the y-axis we have ages. And what we see in the middle is the correlation coefficient between smoking prevalence and the mortality rate in these 10 countries, okay, for the specific combination of the calendar year and age. And what we find is that for most of these combinations, for the vast majority, this correlation is positive. Okay? There are these few kind of black dots in there, and a few black dots indicate where the correlation is actually negative. So a higher smoking prevalence corresponds to a lower mortality rate. Okay? But there are very few. For most of them, this correlation is positive, so the line, even so, it wouldn't be maybe significantly not, it would be statistically not significant, still has a positive slope. And this positive slope we find for almost all years and almost all ages. And that maybe is the important, the first, so to say, important empirical results that we have found. Okay. Now, we wanted to use that fact to model, actually, to find a model which, or to estimate the parameters in a model which explains mortality rates based on smoking prevalence. So here we are back at this basic model that we looked at before. So for every x, fixed t, we have this model for mortality rate in country I given on given smoking prevalence in country I. Okay. Now, the first things we want to estimate, and that's basically all we did, we wanted to estimate the non-smokers' mortality and the smokers' mortality rates, because these rates cannot be observed directly, so we try to estimate those. Okay? And the way we estimate it is by using a maximum likelihood estimation, which is adjusted slightly in a way which is kind of corresponds to a Bayesian setup, where we have assumed that the changes in the log mortality rates here, which I denote by µs and µn, that they are kind of correlated from one year to the next within a cohort. But the important thing is, what we can do is we can estimate MN and MS over time and for different ages in this kind of setup. And all the details, the technical details, they're all in the two papers. And what we get once we've done that are plots like those. So what we have here is we look at the specific age 65, and at the UK data. Okay, and the very top line here. Okay, well, please ignore the dashed lines, so the straight dashed line here. Ignore that and also the dashed line down here. Ignore those for a moment. Okay, come back to those. But the black line here, which has this, which has this variability here. That is the estimated smokers' mortality rates for these calendar years here at age 65. That does not depend on the UK. That's the same for all countries that we looked at. Okay? And at the bottom, what we have here, again, the solid line at the bottom, that's the same rate for non-smokers. So that's the mortality rate for non-smokers, both on a log scale, for non-smokers age 65 in all of these 10 countries. Yeah? They are not country-specific, and these rates are, again, depending on the calendar here. So the first thing we find is that the difference between these two on a log scale is about 1. Yeah? It's increasing, and it's about 1 maybe. So that would correspond to a factor of almost 3. So it would correspond to smokers having a mortality rate at age 65, which is about 3 times that of non-smokers. Okay? The second empirical fact that we find here, which I find quite interesting, is if we look at the smokers' mortality here, again, at this line, the solid line here, there's no obvious trend in there. There's no obvious trend. It doesn't look like necessarily this thing would, so to say, the smokers' mortality rate would decrease over calendar years. For non-smokers, I would argue there's a downward trend in there. And that empirical fact corresponds to something which Doll and Peto have found in their very famous study where they looked at around about 35,000 British doctors. And they found a very similar, so to say, result that smokers' mortality doesn't change much. There's not this strong downward trend in smokers' mortalities that we would find in overall mortality. Now, what about the fit of the model? So again, just the solid lines. Well, what we have is the gray line in the middle. That's the actual observed mortality rate in the UK. It's the England and Wales data, actually, I should say, not the UK. But anyway. And the solid black line in the middle is the fit that the two non-smokers and smokers' mortality rates would give us together with the smoking prevalence. To make this model slightly simpler, we decided to look at a slightly different model where we assume that smokers' mortality indeed does not change over time. And then we fitted this and we got this straight line here, the dashed line here. Okay, so that would correspond to a model where we put into the model that smokers' mortality stays constant. Okay, the dashed line at the bottom is then the corresponding non-smokers' mortality, and the dashed line in the middle, which is hard to see, is again the fit. And they both fit the actual data rather well. Both models fit the actual data rather well, and both, so to say, give a very similar fit. We can do the same exercise for Canada, the other examples that Andrew mentioned at the start. Well, the smokers and the non-smokers' mortality, they don't change in these two pictures. They're exactly the same here in these two pictures, okay? And because they are not country-specific. What changes is the 3 graphs in the middle. Again, the grayish graph is the observed mortality rate in Canada. The black one is the fitted data, assuming that smokers' mortality does change over time, and the dashed one is the model where we assume that smokers' mortality actually stays constant. And you see here that the fit for the constant model is not quite as good, but anyway, it's both of these models, I would argue, fit the data reasonably well, in particular taking into account that, the difference, the fitting error that we still have is something which needs to be explained by other country-specific factors which are not smoking related, and we can maybe still do that. Okay. So how good is the fit in a kind of more, so to say, more quantitative assessment of the fit here? So what we have on top there is again the model. Okay, so this is again our simple model. We have now estimated MNXT and MSXT, and what we now look at is the gamma IXT here. Okay, so the gamma IXT, I is the country, X is age, T is the calendar here. What I can do is I can fix here the age X, okay, and I can fix I. And I have a certain country at a certain age, okay? And then I look at the gamma IXT over time. And I take the average of those, actually the absolute value of the gamma IXT and the average over time, over all the calendar years. And I do that for every I and for every X. And what I get is this plot here, which is on the slide here. Now, it's maybe not enough time to explain this plot in detail, but the thing that's remarkable here is that all these lines come down, so to say, and the levels, so to say, of these lines tell you how much is unexplained in our model. Okay, how much of the mortality rates that we have are unexplained by smoking prevalence. And what we find is that depending on age, in particular for the younger ages, 40 or 50, there's quite a few in these mortality rates which cannot be explained with smoking prevalence. But as soon as we get to, say, pension age, 65, 70 upwards, actually these country-specific effects account for about 10% on average, at least, of mortality rates. Okay? So the fit of the model is much better at higher ages as it is at younger ages, something which you might expect in a sense because, so to say, smoking has this kind of long-term effect on one's health rather than an immediate effect. Okay, I want to finish this with speaking about just a few possible applications here. I mean, the main applications that we have in mind is producing incorporating these results into a scenario generator. That would be the main application. So once you have estimated MN and MS, the non-smokers and the smokers' mortality rates, what you can do is you can fit models, and John has just shown us 6 of these models. You can fit any of these models to MN and to MS, to the non-smokers and smokers' mortality rates, and then combined with maybe some expert opinion or so on smoking prevalence, or a model on smoking prevalence, you can produce a forecast for several populations simultaneously. Okay? And in particular, when it comes to basis risk, a question which was mentioned earlier by Stephen, when it comes to basis risk, that helps a bit, because if you have, say, 2 populations, or 2 or 3 or 4 populations even, if you know something about the different smoking prevalence in these populations, these kind of models can explain some of the basis risk and can also help to quantify the basis risk. And maybe when it then comes to longevity hedging, these kind of models can be used to identify the right hedge ratios that you would need in such a longevity hedge. Okay? So the conclusion, the empirical results clearly not just say that smoking is not good for you, okay? But the empirical results also tell you how you can quantify this effect if you look at populations rather than just individuals. Most of the medical studies, so to say, focus on individuals or very well specified cohorts. But even if you look at entire countries, you can still use smoking to quantify the differences in mortality rates to a certain extent. And that's maybe, the, so to say, the most important result of this research, that that's actually possible. The model fit the observed mortality rates rather well, and they fit them better at older ages. So the country-specific factors that we do not have accounted for here are very small for higher ages. As I said earlier, this methodology can be applied to other factors. So basically, there's nothing special about smoking here. And when it comes to the methods that we have used, you could use other factors. And just to finish this off, here are some of the papers that we produce, or we are still producing, we are still writing on this topic. So the first two are finished papers. One has been published very recently. The other one is unpublished, but is available from us. And then there are two papers in preparation currently. One is the first one here, the common age effect model. This is a model which does not look at smoking. We just look at a model, a consistent model for multiple populations and the mortality in multiple populations. And then the other is a model where we look at smoking as a covariate to model one specific population, which is here England and Wales in this example. And that's it. Thank you.
Thanks very much for your presentation. Something that I'm aware of from epidemiological studies is that it can take some years for the health benefits of smoking cessation to flow through. So I was wondering if you'd given any consideration to historic smoking prevalence and patterns of smoking cessation in your modeling.
No, we have not. And we could, in a sense, look at past smoking prevalence data. That would definitely be a possibility. And in a sense, with the data that are available, the situation is even worse, because if we only look at smoking prevalence data, we cannot distinguish between lifelong non-smokers and current non-smokers, so people who used to smoke, you know. And that makes it even more difficult. But the aim was more to look at a very simple model and use the smoking prevalence data to explain differences between mortality rates in different populations. But you're right, we might look at so to say, past smoking prevalence and use lagged smoking prevalence rather than actual smoking prevalence, and maybe that would be a better way to do it, yeah.
But I would add to that, I mean, it is something that we have discussed, and because if you have the right amount of detail in smoking prevalence and looking at the total deaths and so on, that with the additional outputs from the model, then you can start to estimate, well, how many people are giving up smoking. And then with a more sophisticated model, which is not just smokers and non-smokers, but then amongst the non-smokers, there are in particular people who ceased smoking in the last 5 years. I mean, I'm not sure with your work how many years it takes for you to recover in terms of fully going over, if ever, to non-smoker status. But with some extra work, it's certainly feasible to look at that sort of thing. And then it's a case of, well, does it actually explain much extra in terms of the quality of the fit? But certainly just using that very crude data that we have does deliver some benefits, but it's a matter of can you do better?
Thanks very much. Very interesting. Well, one point of clarification. It wasn't clear to me for the way you were doing your modelling whether you were taking the sort of constant smokers' mortality as an assumption, or was that an output? If you could.
We looked at both. We have two different models. One is where we assume constant smokers' mortality, as you say, but we also look at a different model where we don't have that assumption, but we have an assumption about the correlation between changes in the mortality rates among smokers and non-smokers. The problem is that if you don't put any additional assumptions in, then the smokers' mortality rates and the non-smokers' mortality rates, they will be very volatile.
Yes.
And you need to put some kind of smoothing assumptions in. Now, the most, so to say, the strongest smoothing assumption you can put in is say that one of these rates is constant. You know, that's a very smooth thing then. But the alternative is to say you look at co-movements between the non-smokers rate and the smokers rate. So the assumption being that for a given cohort, if the smokers' mortality rates go up, then it is more likely for the non-smokers' mortality rates also to go up in a certain calendar year. That is the alternative assumption. So what I spoke about is two models, one with constant smokers' mortality and one without.
Okay, so as you might have gathered from the introduction, this is a rather different territory to the people I'm usually speaking to. So thank you to Peter for helping me with some of the vocabulary and introduction. Is there a chance I could get my slides up on the screen? Oh, great, thank you. So the title of the talk is Estimating Risk Profiles for Common Diseases from Environmental and Genetic Risk Factors, but I think it follows on very nicely from Torsten's talk, because what we're really going to think about today is whether genetics has the potential to fill in some of that unexplained noise in your model, the unexplained mortality. So I'm going to give a brief introduction to genetics, to genetic risk prediction. I'm going to talk about the research that we did under the funding in estimating genetic risks of disease. And then most importantly, I'm going to talk about the implications for actuaries. So first of all, a quick introduction to genetics. Apologies to those of you in the audience who know this very well. So genetics is based on the study of DNA, which has this double helix structure here. In some ways, it's very simple because each step on that ladder is one of 4 base pairs, and A, C, G, or T. And this structure was identified by Crick and Watson down here back in 1953. So the structure of DNA has just had its 60th birthday, and you may have heard some of the high-profile television radio programs about that. So the complexity of genetics, and the reason why statisticians like me are involved in studying it, is because the length of this ladder is 3 billion base pairs long. Now, fortunately for us, 99.9% of that is identical across all individuals. Everyone in the same room, everyone in this room will have the same base pair, an A in the same position, and so on. And the interesting part is this 0.1%, which differs between individuals. And it's that 0.1% that gives us our differences in appearance, in behavior, and in what diseases we're likely to suffer from. And as Peter said, much of my research has been in identifying the different genetic contributions to the common diseases. So geneticists like to divide the type of genetic mutations into 2 groups. The one group, the simple group that are easiest to study, are the single gene disorders. So things like Huntington's disease, which is the only one to meet the criteria for the moratorium currently, single gene disorder, cystic fibrosis again, and then the breast cancer genes BRCA1 and BRCA2, where one mutation in either of those genes puts a woman at very high risk of breast cancer. And we've been hearing about BRCA1 a lot recently because Angelina Jolie discovered that she was a carrier of a mutation in BRCA1 and had a preventative mastectomy to decrease her risk of breast cancer. So the characteristics here are that mutations in these genes give you a very high risk of developing a disease. There's a very strong correlation there between genetics and disease. But that's not what most of genetic disease is about. Most of it follows this sort of model, where we have a whole series of genes here involved in the disease, a whole series of environmental factors like the smoking that we've just heard about. And it's not until we consider all of those risk factors, together with interactions within and between them, that we can get a good prediction of whether someone is likely to be affected with a disease or not. And what we've been doing in genetic studies in the last 10 years or so is to start chipping away at this list here to identify some of those genes that contribute to disease. Now, I've shown this with just about 10 genes there. It's becoming clear to us as the studies go on that actually we should be talking about hundreds of different genes, each of which have a modest effect on risk. And I'll show you some examples of that later. I've given a few examples down here: asthma, breast cancer, stroke, heart disease, but really most diseases that have a major burden economically in society or in health generally have this sort of model. So starting to identify the genetic contribution is really quite important. So to put some notation, some genetics terminology on that, what we're looking at mostly is DNA variants called single nucleotide polymorphisms. I'm going to refer to them much more simply as SNPs, which are base pairs like this, which differ in the population. So here we assume that everyone carries a T, C, T, G, G, A, C, but here they can carry either an A or a C. And we call those alleles. So both of those alleles are present in the population. Now, because every individual carries two chromosomes, one inherited maternally, one inherited paternally, at an individual level, what we're interested in is your genotype, what you carry on your two chromosomes. So that might be an AA genotype. You carry two copies of the A allele here. You might carry one each of those, or you might carry two copies of the C allele. And so this gives us three different possibilities for each individual of the genotype that they carry: an AA, an AC, or a CC. And many of my research studies recently have been trying to identify these variants here that play a risk in disease. So the studies that we carry out are very simple case control studies. We identify a set of cases who are affected with the disease, a set of controls who are unaffected, and we genotype them. So this ideogram just shows you genotypes at this particular SNP, three different colored balls there. And you can see, just comparing the colors, that many more of the cases carry the blue, the C allele here, than the controls, who are predominantly this CC genotype. So this suggests that at this site in the DNA, at this SNP, carrying allele C increases your risk of disease, because that allele is seen more commonly in cases than in controls. So the studies that we carry out look not just at a single SNP, as we did on the previous slide, but at a set of 500,000 SNPs across the genome. We genotype, we test each of those in our panels of cases and controls for different disorders. And so we identify different sites, subsets of those SNPs that seem to contribute to risk of disease. And there's two parameters, the two pieces of information that we want to know about that SNP. We want to know the odds ratio of disease, so the severity, how much carrying a particular SNP allele increases your risk of disease. And then we want to know how prevalent, how frequent that is in the population. And then from that information, we can calculate someone's genetic risk of developing disease. So to give you a quick example, in breast cancer, now we now have over 75 SNPs identified contributing the risk of breast cancer. I'm just going to look at a few here. So this is the first SNP that seems to have the most major effect. SNPs are always called by RS and a long string of numbers. This particular one lies near a gene called FGFR2. The risk allele is an A allele. And in the population, we have, as I've said, three types of people: those that carry 0, 1, or 2 copies of the A allele. The 0 is our baseline group. And if you carry one copy of that allele, your odds ratio is 1.3 compared to someone who carries neither. 2 copies, an odds ratio of 1.8, so a slightly less than twofold increased risk of breast cancer. And then the second SNP lies near a gene called TOX3. Again, the risk allele is an A, and you can see the odds ratios. Again, each allele has a fairly modest effect in risk, and it's combining across these SNPs that our information is going to come from. And so you can work your way down the list. I've just included 5 here. That's what's going on in the population. At an individual level, we want to know what an individual's risk, what their genotype is, and how that affects their risk of breast cancer. So by an individual, we can just look for each of these SNPs, how many risk alleles they carried there, and then read off from the table their odds ratios at each of those SNPs. So at the first SNP, the odds ratio is 1 because they carry, this woman carries no risk alleles, 1.28 here, and so on, working down the table. We assume that each of those SNPs contributes independently to breast cancer, so there's no correlation between them. And then to combine, we can just multiply the odds ratios down this column here. So the product of the odds ratios there is 2.38. Now, we have to do a bit of rescaling because the baseline there is someone that carries a whole string of zeros down here. And actually, because these SNPs are fairly common in the population, most people carry some risk variance. So what we do is rescale that so the odds ratio is compared to an average member of the population. And then if you look at a risk distribution in the population, you get a distribution that's like this. This is our baseline risk for our average member of the population. And you can see most people have a risk that's fairly close to that. At the bottom end, these are the people that carry few risk alleles. They've substantially reduced their risk of breast cancer. At the top end are the ones that we're really interested in. These are the women that carry many risk alleles, and so they have a substantially increased risk of breast cancer. And what use we can put this information to really depends on this scale down the bottom here. So if this top end, that light blue triangle, is identifying a woman that has, say, a 1.5 or 2-fold increased risk of breast cancer, that's not particularly useful. But if this is a 5 or 10-fold increased risk, that could be of use to both to you and to the woman herself. Now, there are companies out there that will tell you your risk of these information, of these SNPs. You can send off your DNA to 23andMe, and they will email back your risk of breast cancer and heart disease and all sorts of different disorders. There are also companies in the UK. StoreGene is one that estimates your risk of coronary heart disease, and I know they've been marketing themselves to the pensions side. So what we've been doing is developing methods to estimate risk of disease, both using genetics, as I've talked about, and environmental risk factors. And then we develop methodology to incorporate confidence intervals, because very often when these values are reported, they're just reported as point estimates, and you have very little idea of the variability involved. We've developed risk software, Regent, written in R, and then we've evaluated the utility of the models that we've developed. So to start to go into the genetics part in more detail, we take the SNPs that we know are associated with disease, and we extract from the literature the allele frequency, P, and then the odds ratio, as we've been talking about. So this is the level of severity. The usual model we use just models this as a square for the carriers of 2 alleles. But that's not, the method will work beyond that. We need a disease prevalence R if we want to turn these back into absolute risks. And then we assume very simply that the risks are multiplicative across the different SNPs. And then you can calculate fairly simply the probability that someone is diseased, is affected with the disease, given their SNP genotypes, is just the product of risks and the frequency, that term there. For the environment, we look for the odds ratio of the environmental risk factor together with the confidence interval. We also need an exposure prevalence. And then we can put that together again as a multiplicative term here, just whether someone is exposed or not. And again, we assume that environmental risk factors are independent. We can put that together into a complete risk model, combining the genetic and the environmental risk factor, again, assuming independence. And then we calculate confidence intervals. Because the variability for these comes from so many different sources, the risk estimates, the frequencies, the genetics, and the environment, there's no closed form for the confidence intervals, and so we use simulation studies to get empirical confidence intervals. So to give you an example of how this works, I'm just going to cut down even further to looking at 3 SNPs here with the allele frequencies and the odds ratios. Now, we have 3 different genotypes at 3 SNPs, so that gives us 27 possibilities in the population. They're just listed here. This one here is our average individual. So these people have slightly reduced risk. These people have increased risk. More easily, we'll put that graphically. So across the bottom are our 27 different risk groups, and a combined odds ratio, relative risk on the y-axis. This is our average individual here with their confidence interval. And what we do to categorize people into risks, we look at how the confidence intervals for each of these risk groups, these genotype groups, overlap. And any that overlaps with our average individual, we say they are of average risk. There's no statistical evidence that they differ from the baseline. Those that have reduced risk down here, their confidence intervals are distinct from the average person. And then moving upwards, we can get an elevated risk group, and then beyond that to a high-risk group, which we don't, with just 3 SNPs, we can't manage to tease out. So that allows us to put people into different risk categories from the SNP information. When you go beyond 3 up to multiple SNPs, you get more of a continuum like this. This is 71 SNPs in Crohn's disease. So these are our reduced risk in green, our average risk in blue, and you can see that we now pull out just over 10% of the population at the top who are of increased risk compared to the baseline individual. And we've developed software to do this that we've called Regent. This is open access software. You can download it from the CRAN website. And it's been published in a risk report here. The software does 2 things. It does the population level risk, which is what I've talked about on the previous slides, and then it will calculate an individual's level of risk if you input genotypes and their environmental risk factors, which can be multi-level ones. And we've illustrated that using colon cancer in a paper that came out just a few months ago. What I'm going to do for the last few slides of the talk is to show how this can be applied to diseases that you might be interested in. So I've taken late onset disorders, coronary artery disease, colorectal cancer, and type 2 diabetes. I've identified the SNPs, the genetic component that's most strongly associated with disease, and I've modeled the genetic profiles in the population. And then looked at how we can interpret that to see if this is really giving us useful information, if that scale on the graph that I showed really goes high enough to be of value. I should say that here I'm going to talk just about the genetic risk, because we know a fair amount about the environmental risk factors for these disorders. And I think the interesting question is whether the genetics gives us any added information. One of the ways that we assess these models is through the receiver operating characteristic curve. And what this method does is it takes 2 curves of the risk level for controls and cases of our disorder and looks at those that are classified as true positive or false positive. And then you plot a curve like this of sensitivity, so true positive against a false positive, 1 minus the specificity here. And the idea is that you move this cutoff for the test across these distributions, and at every point, you draw a point on this curve here of the pairs of sensitivity against 1 minus specificity. Now, what you want here is a test that leaps straight up from 0 down here to 100% sensitivity and then moves straight across the top. And the way that we assess that is by looking at the area under the curve. So the diagonal line here is something that has no predictive value and gives an area under the curve of 1/2, and the maximum would be 1 for a test that does exactly as we want. So the other way of interpreting that is that the AUC gives you the probability that if you have a case and a control, you can correctly assign them to the case or control group using just their genetics. And I think that'll become clear on the next slide. So these are those 3 disorders. The number of SNPs that we've identified for each of them varies, just depends how fast genetic studies have moved on and how major the effect is, so how easy it is to detect the SNPs. These values here are the area under the curve. They come out to close to 0.6 for each of those. Now remember, that's the probability that given we had a case of colorectal cancer and a control, that we would identify them correctly from their genetics. So that's a pretty pathetic classification statistic. For any sort of medical use, we certainly want this to be over 0.9 and probably closer to 0.95. So that's the first indication that there's not a lot of information here. And then the next 2 graphs, the next 2 columns, I've just put the proportion of the population who were at over 2 or 3-fold increased risk of disease from their genetic contribution, from these SNPs that we've modeled. And again, you can see that's very disappointing, less than 2% for each of those. None of those have a 3-fold increased risk of disease. And so although all of these disorders are fairly common in the population, we're not really identifying those that are at increased risk from their genetic component. Now, there are some disorders that we can do that with rather more successfully. I've put on the bottom of the graph age-related macular degeneration, which is late-onset blindness, and Crohn's disease, which we've been very successful at identifying genes for. And you can see that the AUC values and the proportion that reach those cutoffs is much higher. So genetics for some disorders is working fairly well, but for the late onset disorders that we're really interested in being able to do, we're not being so successful. And to put that into context, this slide shows the relative risk for those in the top 5% of the genetic risk. So I've taken off the top 5% of the population and said, well, what's their minimum genetic risk? So this goes from about 1.6 to 1.7 upwards. So it's a fairly modest increased risk, even for the top 5% of the population. And then what I've done is compared that to some of the other risk factors that we know about for these disorders. So for family history risk factor, if someone has an affected sibling, then we know that they're at 3-fold increased risk of coronary artery disease, say. So that is much more predictive than the genetics are currently. And I've just listed some of the epidemiological risk factors here. And again, the risks tend to be much higher than we're getting from the genetics. So in conclusion, the genetic studies have made huge scientific progress. I mean, I'm certainly doing things that we wouldn't have dreamt possible in our labs, in our clinics 5 or 10 years ago. And we're identifying genes that give us new insights on the disease. They'll give us new targets for drug development. But the information seems to be very limited when we want to use it for prediction. And there's 2 reasons for that, really. One is that these are polygenic disorders. There are hundreds of genes involved, each of which having a tiny effect on risk, and we're really only starting to identify them. And then the second reason is a more technical genetic one, is that very often we're not identifying the true mutation, we're identifying something that's correlated with it, that lies in the same genetic region. So the genetic studies that we're doing are not yet very precise. And so currently the conclusion really has to be that genetics is not there yet, and we get much better prediction of these diseases by using factors like family history, which of course includes some of the genetic component, and environmental or preclinical risk factors. This is work that's been carried out at King's College London in collaboration by colleagues Graham Goddard, Dan Crouch and Jane Yarnell, with of course funding for the Institute and Faculty of Actuaries. And I'll finish there. I'm happy to take questions.
Thank you very much.
Well, thank you very much. Very, very interesting. A few sort of questions quickly we've answered. One is, presumably this is all about incidence of the definition as opposed to treatment. It'd be interesting what your thoughts are, whether there's been any sort of similar research about the influence of genetics on the successful treatment.
Okay, so yes, I've been talking about incidence, susceptibility to disease. We also have research programs, what we call pharmacogenetics, so looking at how genetics can help us treat disease. And although we had high hopes in those that there would be more successful prediction, again, we're just starting to chip away at that, and so it hasn't, apart from a few very high-profile results, like in some of the cancers, where looking at tumour genetics very much directs treatment. For most drugs that people are treated with, we haven't yet got a handle on the genetics susceptibility, but we think it does exist.
One of the questions was, this is all UK, or is it a combination of different?
It's a combination of different. The genetic studies have mostly been carried out in white, Caucasian, European ancestry populations. So many of the studies we've taken this information from US, UK and European genetic research studies. There doesn't seem to be a big difference across populations within the same ethnic group. Across ethnic groups, yes, there are differences.
And the last little question was, presumably, family history is effectively genetic, it just isn't genetics in the sense that you're explicitly modelling to us what your opinion is.
Yeah, so I think family history is a bit of a catch-all. So some of it is genetics, some of it will be the genetics that we've modelled here, some of it will be the unmodelled genetics, and some of it will be common environment. So we know that smoking runs in families, and so that will come into the family history as well. So smoking, diet, all of those things that are about common environment will contribute to the family history component.
Thank you. Why are the effects of all the mutations given equal weighting when you combine them to look at the combined risk?
Well, they're not actually given equal weighting because we use the odds ratio to combine with. So a variant that substantially increases risk will have a much bigger effect in that model. And actually what we find, if you rank the SNPs by their effect size and their frequency, so a contribution to disease, by the time you've modelled the first 10 or 20, the ones after that are having very little effect on risk because they have such a minor, the odds ratio are very low.
But they're assumed independent in the sense that you're not looking at particular combinations of
No,
SNPs.
you're right. They're assumed independent. Most of these SNPs are well separated on the genome, so there's no reason that they should be inherited together. And that's the sort of thing we can test very easily in our studies. And currently, that assumption fits the model well. As we identify more and more, it may not, but currently it seems a reasonable assumption.
A couple of questions. Are there any studies that combine the environmental and genetic factors, so on the subject where you sort of know and can test the assumption of independence?
Yeah, I mean, a lot of studies do collect detailed clinical information as well as DNA, and so we have that information. Currently, as with the genetics, assuming independence between genes and environment is a model that fits our data. There are reasons to think that that's probably not true as we get through to the next level of resolution, and we find probably these true causal variants rather than just the convenient SNPs that we're genotyping. But currently, from what I was doing, it's a reasonable strategy.
And then a follow-up question, thinking sort of from the reverse side, from the annuities, people who carry favourable genetic predisposition, do you foresee a time that that would become a common practice, that someone could submit that information to get better insurance terms?
Well, I mean, I'm probably not the right person to ask about the actuarial question, but yes, I've focused on high-risk people here. But of course, the symmetry of the graph is that there will be a similar proportion of people at low risk who at the moment we can't identify very accurately, but we may well be able to do over the next few years.
I'm going to have two sort of quick questions. Oh. So just pick up on that last one about the symmetry of the graph. Was it actually presumably a symmetry in terms of where the sort of alleles were sort of good or bad as opposed to the actual effects? I wonder whether the effect graph would be symmetrical.
They come out fairly symmetrical, partly because we're just adding together many different, very small effects. If you have large effects, that's not quite true. You get a tail.
And then the other question was if you were the Oxford Wellcome sort of genetical map of the UK, which came out 1 or 2 years ago.
People of the British Isles, the Polish study.
Yes. I was wondering whether you're aware of any work's been done on that and trying to sort of find a connection between that and either particular condition, propensities, or mortality, or anything along those lines.
Yeah, I haven't seen any work that's come out on that. I mean, certainly when you look at different areas in the UK, SNP frequencies differ. So, the genetics of Scotland is very different to the genetics of Cornwall. But we haven't really seen how much that's gone through into the genetics of disease or not. So I don't have an answer.
Well, I also have a question for Catherine. So you go first, and then.
Just a couple of points following up on the discussion in John's talk that I've done some work on Bayesian modelling myself, although more on the two population modelling that Matthew asked about. But so the Bayesian is certainly it is a time-consuming method computationally, but I've certainly found it's a very effective method for dealing with certain things. So two population modelling and basis risk is one of those. But other things that it is good for is for dealing with small populations where you need to sort of, to some extent, you're redressing the balance between the sort of time series effects which are embedded in the period effects and also the cohort effects, as well as, say, things like having missing data, so that if you're trying to model one pension plan alongside the national population, then you have much more data for the national population. And so you can use or put in effectively missing data and sort of, in some sense, piggyback your pension fund off the fact that you've got much more data and more reliable data for the national population. So in some sense, you can get improved projections for various methods, for various reasons, for smaller populations. And in the basis risk context, I mean, we've again, with David Blake and Kevin Dowd and the Life Metrics group, we, a few years ago, published some work as a starting point on the basis risk question with the two populations, and that was on the M3 model that John mentioned earlier. The other question in that discussion was about the higher ages, and of course one of the reasons why people tend to avoid using the higher ages is because of perhaps a bit of an unreliability in the data, and of course that was seen last year with the ONS revising its data, and so that's something I'm just starting to look at now, is to see, well, first of all, with the models that were being talked about earlier, well, what if you use the data that you've got at the higher ages that are produced by the ONS, if you put that in, fit all of these models, what sorts of impact does that have on the forecasts that you're getting from these models? And this is very much work in progress, but at least the sort of preliminary conclusions are that there is not a massive impact on the forecasts. What you do get are some small changes in the sort of base tables, particularly at the high ages. But broadly speaking, the sort of trends and the sort of widths or the levels of uncertainty are not massively changed. But then the next steps are then to think, well, what's to stop the ONS revising its data again in 10 years' time or whatever, as well as other issues such as clearly with the ONS and many other populations that the exposures data are just uncertain. They're not as accurate as we would like to be, and perhaps that's part of, John, in your discussion, you were talking about the Poisson distribution and whether that's the right distribution. Of course, you then have to think, well, why is it not Poisson? And one reason perhaps is that the exposures themselves are not perfect numbers. So as an avenue for future research, I think that's could be quite fruitful, and it might help us to understand better, what are the underlying dynamics in the past as well as what's going to happen in the future.
Thank you, Andrew. I did have a question for Catherine. I think I take comfort from your presentation around kind of scope for anti-selection in the life assurance market. But then you kind of, in your summary slides, you kind of made the comment, the things that have changed in the past 5 years are substantial, and you were doing things now that you never thought you'd be able to do 5 years ago. And then on your second bullet, you very much kind of couched everything in terms of currently we can't do this and currently we can't do that. So kind of pushing on, gazing into your crystal ball, are there things that you could foresee happening over kind of 5-10 years that actually does make genetics far more predictive than what we're currently seeing?
I think what's going to come next is that we're going to move on from these 500,000 SNPs that we were talking about across the genome, and we're going to be sequencing people start to finish. So we'll get 3 billion base pairs. And so that's just going to give us a lot more scope to fill in the gaps in these studies. It's not going to get away from the fact that there are multiple, we know hundreds, maybe thousands of different contributors. So that number's not going to change, but we are going to identify them, with more precision. And I suspect if not 5, then certainly 10 years, we're going to be walking around with our sequence, on a USB stick. But the technology is there. But actually interpreting that data is going to be much harder, and so I think that's going to be, ongoing for many years after that.
Okay, thank you. Andrew, while you were talking about Bayesian statistics there, I was trying to think back to my actuarial education, actually, and I'm not convinced it's an area where there's an awful lot of time spent, but as you said, there's kind of a myriad of applications for Bayesian statistics there. I mean, is that an area where you think actuaries are deficient in our kind of training and background?
Well, I don't know the finer detail of what's there currently in the syllabus, although except to think that it probably is a very brief introduction to the subject, and it sort of feeds into decision theory, for example. But then I think that's the basic introduction in the core technical subjects. But then I guess there's a very big leap from the basics of Bayesian statistics through to the MC methods that were being talked about, which is very much touchy-feely, I would guess, in terms of doing the job for any particular application. You can teach students a little bit about it, and I mean at university we do have a whole course on computational Bayesian methods, and of course it's a matter of from the actuarial perspective, that would be very much treated as a specialism, and I think it does require a kind of range of skills to be able to do that sort of job well. So certainly a very good background in statistics, but you also need to have very strong computational skills, a fair amount of intuition, and a lot of stamina and perseverance it takes many efforts at programming to actually get these things to actually work. But ultimately, you know, there's a lot of satisfaction when you actually get to the end of a working program that does actually produce consistent results from for different, say, mortality models or whatever. But I think in terms of education, it's probably the sort of thing where it's more at a post-qualification level that you need to be thinking about CPD, just to introduce people to the potential of these methods. You know, the mortality is one area, but you know, I'm sure that there's plenty of it going on perhaps in the non-life area as well, where there's an awful lot of good statistical work that's going on in that area.
I can't talk about actuarial education in particular, or even particularly about actuarial modelling, but there has been an increasing tendency across all areas of practical modelling for people to be interested in what, as Bayesians would call, hierarchical models, but you can also address within a likelihood framework, random effects models, mixed models, multi-level models. They are particularly naturally addressed within a Bayesian framework because it's a case of having variable levels of uncertainty. And in fact, these mortality models are just particular cases, because when I wrote down this model as having a rate model and then a projection model, it's essentially a two-stage process. Well, there's lots of practical areas where you model things in multiple stages and you have a hierarchy. And in fact, it's one of the it's a real tool for modelling in a sense, is that it's difficult to model typically things that have complex dependence. So the way in which we model things that have complex dependence is essentially by constructing a structure that's conditionally independent, and then the complex dependence is kind of what you get when you would marginalise across that structure, but you don't. You model it as a series of conditionally independent steps in a hierarchy. Now you don't have to do that in a Bayesian way, but you can fit mixed models in other ways, but there's certainly a lot to be recommended by hierarchical modelling, by thinking about the interdependence of your various the interdependence, how your model may be specified as an interdependent nested structure.
Well, thanks. Just on the subject of Bayes, then, I'm sort of trying to think back again to my university days, which is quite tricky, actually. But presumably, to get it to work, you need the prior distribution. So I wonder whether the assumption about that is actually introducing a significant form of model risk, or if it's normally a fairly obvious sort of qualitative decision.
Well, it comes in two ways. I mean, again, it's thinking about this hierarchical structure. The second part of the model you can think as the prior distribution for the first part, of course. So you've got your rate model with your kappa parameters as I had them there, your time coefficients, some of which you observe and some of which you want to project. Now, the fact that you've got a time series model for those, that actually is in some sense, is part of your prior distribution for those. Now, it's built up in two stages because that model itself also has parameters which you have to specify. And those parameters in a Bayes approach, we give prior distributions. I think the prior sensitivity issue, if you're just fitting a single model, typically is of less import than it is when you do the kind of thing that I was talking about, and it's an issue to do with Bayesian inference under model uncertainty, which I didn't talk about today, which is you can't just throw conventional diffuse priors at your parameters because that marginal likelihood, the thing that you have to calculate, essentially the prior normalizing constant comes into it in a way in which it doesn't in standard single model inference. So there is a sort of technicality, sort of subtlety, which I didn't have time to talk about today, but which is in the paper, about the care that's required in a multi-model Bayesian setup. But in a single model case, if you wanted to just do a Bayes model in a single case, you've got a lot of data there. Unless you've got, in certain aspects, the prior will come into play, so that the fact that you've got a time series model will induce some kind of smoothing, which is almost certainly what you want. That's why it's there. But the other aspects of the prior, with a large amount of data that you do have, are probably not going to be you're probably not going to have a great deal of sensitivity.
So also the prior distribution would be the place where the expert judgment, in a sense, would come in. Yeah. The expert opinion about what people think about the distribution of a certain parameter, and then that opinion would be adjusted by the data in the second step. So far, it's a very kind of natural thing, very natural way to estimate parameters and to get posterior distribution for parameters.
as one example, the two population modelling that I mentioned, where I had used Bayesian methods, my preference is to use as much as possible uninformative prior distributions, just in order that the data can speak for itself. But then sometimes you're going to get results which are, particularly in the forecasting, which don't quite conform to what your expert judgment would say ought to be true. So, for example, with the two population modelling, you say have a wealthy and healthy subpopulation and the national population mortality rates up here. So as you forecast those, you would expect one to remain below the other, but on the other hand, you don't want them to gradually drift further and further apart, or indeed to cross over, for example. So you can use a prior distribution to deal with that sort of thing, to build in what are reasonable assumptions into your model. And if the basic data doesn't produce that sort of results, then you can tweak the prior distribution in order to deal with that sort of feature. But it depends on how you do it. Some people will impose a prior distribution at the outset and then not fiddle about with it. And I'm more pragmatic when it comes to Bayesian. It's a very useful tool for some of the reasons that John outlined in his talk, in terms of just model averaging, but also just things like incorporating parameter uncertainty into the forecasts.
And I think the other thing to say is that where you really gain from the prior is not necessarily in particular values of prior distribution parameters you plug in, but it's in the structure of the prior. So the sort of borrowing of strength issue is something that Andrew talked about earlier, where you've got lots of data to learn about where you've not got much data. Well, the reason that happens typically is you've made some prior assumption that perhaps you've got these three groups are all conditionally independent given the same parameter, and using the fact that that's the same parameter to learn about. Not the value of that parameter, because if you've got lots of data in the two groups, you don't really learn much about the value of that parameter from the data. But the fact that the third group you're assuming is similar, that's where you get the borrowing of strength. So it's the structure rather than the actual numerical values you plug in.